Good morning, everyone. With us this morning are Melanie Stein, who is the Director of Communications at PAA, and I'm Skip Wagner, and work with training and service operations. We're going to be discussing some basic principles of electricity, which actually is nothing more than electricity will flow in the easiest and less resistance direction. So electricity will always flow in the path of least resistance. And it's that theory that we have to keep in mind this morning. And to start off, I'm going to show you a very simple switching device of electricity, and this would be a set of ignition points that we've used for many, many years. And this was a switching device opening and closing that controlled spark to the spark plugs. Certainly we do not use ignition points anymore. We use a module and a semiconductor, and normally the coil is now located on top of the spark plug and actually controls the spark to the spark plug electronically. But initially, as the engine started, and from the very beginning in the late 1800s, they used a switching device such as this. And in many cases, electronic systems today are actually kind of the same device. We have here a schematic of a turn signal system and parking lights. Here you have a parking light switch, which of course would be controlled right on the instrument panel. We have a positive and a negative battery source. Negative, of course, is ground. Positive would be feed. To turn the parking lights on, you're just going to energize the switch, and you now have the parking lights. This light is indicating a side marker, and the bottom light is indicating the actual front parking light. Now, the issue is the flow of electricity. We have the switch turned on. The switch is energized, and we now have electricity flowing down to this connector, across from this connector to the side marker light, and also it is going down to the feed is going down, continuing on to the parking light, which is just a simple 3157 bulb, and the base of the bulb is grounded, and of course travels through the ground circuit to the negative side of the battery. Now this initial circuit is very simple. You have it going down to the low side of the parking light bulb on the 3157 and continuing on to ground. Now the question is, where does this side marker bulb get its ground circuit? Certainly the feed circuit is coming in, and this is just a simple 194 bulb, and you're coming into the one contact of the bulb, and it goes through the filament of the bulb and comes out. But where does this bulb get its ground circuit? And the answer to that is, of course, is that, again, electricity is going to travel in the path of least resistance, and electricity travels down through this wire, actually to the contact, to the turn signal contact of the 3157 bulb. So the one filament, and this is a double filament bulb, the one filament, of course, is lighted and it's receiving its ground circuit. The other filament is not lighted, but the ground, it's using the ground circuit from that particular bulb, and it is using the high filament of this bulb in order to supply the ground circuit for the side parking light. So the the issue is that electricity follows the path of least resistance, and the filament in this bulb supplies that least resistance path. Now, now this could travel across here to this bulb and seek ground, and all that we would have to do is to just lightly loosen this terminal. That creates an additional resistance, and as a result of that, now the voltage traveling to this bulb will find the path much easier to travel across this circuit to ground rather than going down into the filament of the high filament of the 11 or the 3157 bulb. So again, what we did by loosening this contact is just creating a lower resistance traveling straight across from the parking light bulb. Now, we used to see this many times, and still do to some degree, that when we had a bad contact, or in fact if we had a bulb go bad in a turn signal, that we would see some bleeding in the turn signal indicator on the instrument panel when in fact the turn signals were not turned on. So again, all we need to do is to tighten this connector, lower the resistance down to the bulb, and then of course the instrument light will go off, and that would be the same as if we had a bulb that was burned out on the turn signal. Okay, the other principle is the parking lights have been turned off, and you have activated the turn signal. Now this is a flasher mechanism that is making these lights blink. Flashers, of course, and this is again nothing more than a switching device. This turns the lights on and off, very similar to the old type ignition point theory. And this is just electronic a switching device with a bimetal spring that heats up and opens and closes very quickly. Actually, it's nothing but a very weak relay. And this now is your switching device. In current models vehicles, they're going to be using a semiconductor and also a body control module, which does the same thing as the turn signal. So this is a mechanical device. The devices that we're using today would be semiconductors and body control modules. But the turn signal lever has been activated. You have a side marker blinking. Of course, you have the instrument panel light blinking, indicating that the turn signals are on, and you have the high filament of the turn signal bulb in the front of the vehicle blinking, indicating that the vehicle is going to be making a turn. Now, again, the circuit for this would be coming into the flasher. When the flasher points make contact, you're going to be coming down to this terminal. It'll cross over into the instrument panel and seeking ground. It's going to come down into this way, and it's going to cut across to the other side of the 194 bulb, and it is going to seek ground through the lower terminal filament of the parking light bulb. So the flow of electricity is going to now go this way and down to the seeking ground to the base of the turn signal bulb. Now the third issue is we activate the parking lights along with the turn signals, and you see that now the side marker and the parking light are going to sequence rather than come on both at the same time. Your dash light indicates that the turn signal is on. The marker light of course is on, and the turn signal is also on because both the parking light and the turn signal is on. But the question would be, why are these two bulbs sequencing. And you will notice that your side marker will only come on when the high filament of the parking light is actually off. So, as originally explained, the ground path would be down to this terminal, across to the marker light, and across to this terminal. But where does it seek its ground? And the ground again is going to come down into here, into the high filament of the parking light bulb, and this light will only light when it has ability to seek ground, and that would be when the turn signal bulb is on the turned off position. So that's the whole sequence of the non-sequential parking and side marker lights. Again, this is a study of electricity, in that the electricity will flow in the path of least resistance, and anytime you create an additional resistance pattern, then you'll see you disrupt the entire flow of electricity. This, of course, is now creating a series circuit where you have the electricity flowing from the positive side across the bulb, and it continues through a series into the instrument light, and of course it's going to seek ground. So many of these principles are all done through semiconductors and through body control modules, but this is actually the mechanical version of what we are now seeing as the electronic. So it's important to understand how electricity is going to flow. You see the actual mechanical switching devices working, which now is accomplished through semiconductors and body control modules.